Okay, calculate acceleration in connected multi-body systems. This is in 13D. So, what do I mean by multi-body system? I mean that you've got multiple parts and connected. In this case, we're just going to think of it as a perfect string, or rope, something along those lines, or rod, any of those sorts of things. So, here I've got three bodies all connected by these strings, rods, whatever you want to call them. We're going to imagine that these things are perfectly massless, just for simplicity. So I've got three things. If one of them is being pulled along, then presumably all three will get pulled along. We're going to assume that these strings, although they're massless, they have infinite strength as well, so we don't have to deal with any of their material properties. Brilliant. What I would have you consider is, imagine these are string for now. If I pull this one across, this string will all of a sudden be tight, it'll have tension in it. Okay, well, which way does that tension go? Well, you might think, okay, I'm pulling this way, so I should have an equal and opposite reaction going that way. And that's true, but you have to be a little bit careful because you'll have tension in this rope, but I'm pulling this way, so the tension will go this way for this one. Okay. But if I think about this guy for a second, he's being pulled by the rope, so there must be tension pulling that way. So you've got, with tension, depending on what part of it you're looking at, you can consider it being in either direction, or in both directions simultaneously, so just be a little bit careful with your thinking. Either way, that's happening, great. Cool, I've got these two objects. Okay, well, if this one's getting pulled, this one will move along with it. Well, this string will be in tension as well, and so that'll bring this third block with it. Great, so I'm going to have this one getting pulled back by this string, and this one being pulled forward by that string. Okay, great. So I've got tension in the string. Now the question is this tension going to be the same as that tension? It's like, well, it's all one body, so maybe they're equal, but if we think about it for a little bit longer, we can get some intuitive sense for that's definitely not going to be true. Imagine that this was just like 10 grams of mass, this was 10 kilos of mass, and this was 10 kilos of mass. Okay, if I imagine pulling 10 kilos of mass across these two, that string had better be strong enough. Because if I'm trying to pull it, it doesn't really matter how massive this is, but how massive this is. If I try to pull this along, if this is a really weak string, it's just going to snap straight away, which suggests that there must be a fair whack of tension in that. But if I have a 10 kilogram mass here and I pull that along, and this is only 10 grams, this will pull along no problem. Like, that would have to be incredibly weak. It'd have to be made of tissue paper or something before that would rip apart. So that tells us that these tensions aren't going to be the same, just intuitively. So the more stuff you have to carry, the bigger the tension is, and this tension is actually going to be carrying both these masses. So this tension, assuming that this is the one that's moving forward, this tension will always be higher than this tension. Brilliant. Well, what if we lay them up over a pulley? So because we've instilled magical rope for these that has no mass and infinite strength, we're going to do a similar thing with the pulley. It's going to be a massless pulley, so we don't have to worry about losing energy to rotational inertia or anything. And it also has zero friction, which is a very handy property. So we get to invoke magic, even when we're doing basic physics, because otherwise it becomes too painful. So I've got some masses on strings. Hopefully you would agree that whichever, unless there's an initial velocity, which we're going to leave out for now, if I just have these masses here, if they balance perfectly, then everything would stay still. Okay, great. Well, there would have to be gravity affecting everything. Great. Assuming everything is staying still for now, well, then there would have to be a tension pulling up this way. Call that T1. Great. Well, we've established that the tension in the string must be the same in both directions, so there must be T1 going down. Great. We've also established, this is T2, that this tension should be different to this one. Since this piece of string is supporting the weight of this mass and this mass, this tension should, T2, should be higher than T1 in magnitude. Great. If we have this going around here, since it's one of these nice magic pulleys, the tension on this should be the same. Now, something to be careful about, this T2 points up and this T2 also points up. So we have to be a little bit careful when we're assigning positive negatives here. But so long as you're conscious of it, you're okay. If this total mg, total down onto the reds, will equal this, so long as these masses add to this mass, the T1s will cancel when you're adding up all the vectors. So we get 2 TTs coming up, 2 reds equals the 1 red on this side, and the 2 T1s cancel each other out. Everything balances. If there is an imbalance, then all of the objects, whichever side is heavier, they're all going to go that way. So if these two are heavier together, then the whole thing will rotate that way. If this one's heavier, the whole thing will rotate that way. Either way, everything will rotate together at the same rate. So you'll always have all the acceleration. So acceleration of object A has to equal acceleration object B has to equal acceleration object C. Beautiful, yes, good. Another thing to be careful about, that acceleration could be going either way, so you have to be careful with positive negative errors. Beautiful. Okay, well, let's do a train. So I'm going to say this is my train engine. So that's the part A. Part B and C are just dead weight carriers. So that's that. Great. We're going to have train A weighs 1 ton, carriage B 2 tons, carriage C 3 tons. Okay, we don't know how much force the engine is providing, so that's question mark. This is probably a bit too high for a railway, but it doesn't matter. Coefficient of friction 0.1, and I'm going to make gravity 10 meters per second, just so we've got nice round numbers, because if we make it 9.8, it just makes the numbers ugly for no added clarity in learning it. Cool, so we've got force diagrams going. Our engine's going to be trying to pull off forward. We're going to assume that this is on nice flat land, because that just adds in one more complication that we don't need right now. So we've got gravity pushing down, and we've got the normal force pushing back up. These two will cancel each other out, so I don't actually care what they are, per se. There'll be some friction on the tracks, okay? So I've got that orange for that friction. And then I'll also have this tension pulling this way on A, this tension pulling that way on B. Similar story with these. T1 should be greater than T2, but figure that out later. Great. Similar story for the rest of them. Okay, great. Now, you might be tempted to say, well, this is where the force is happening, so I should start here. It's actually easiest to start with the last body first, because there's the least things going on. So, green and red, they're going to cancel each other out because we're on flat ground, so we don't even have to worry about those. Friction, okay, frictional force on carriage C. So 0.1 times 10 times 3,000, so constant times normal force, which is mg in this case, since they're equal. So I've got mg. I put that in green just to remind you that that's normal force, not gravitational force necessarily. But in this case they have to be equal. Great, so that's our friction on C. T2, well, whatever this thing is doing, if it's going to move at all, then we have to at least overcome the friction. If we're going to accelerate at all, then we would have to have F equals ma, so A times mass would give me my force of acceleration, which also has to be transferred through this string, so that gets added in to T2. Beautiful. Continuing on, similar story for B. We've got friction. Turns out that's 2,000. By the way, the fact that the mass is 3,000 and the friction was 3,000 is mild coincidence. It's by choosing these 0.1s and 10s, that all cancels out. In reality, they're not likely to be the exact same, hence why I've written them in different colours, just to try to make that a bit clear. Cool, so we've got friction for carriage B by itself is 2,000. Okay, great. Carriage B is being pulled by T1, but T1 would have to overcome both T2 and this friction. So we've got the friction plus T2, and on top of that, if the thing is going to accelerate at all, we'd have to take care of that force as well. Great, simplifying down, done. Cool, now we get to the front finally. Friction for A, calculated as before. This has to overcome, did add that in twice. T1 plus T2. I may have added that in twice, I may not have. Depends how dumb I was. No, I've already included it. I just wrote it for no reason. Good. Sorry about that. So we've got the tension in 1. And I'll fix that up now. Cool. So, forces involved, we've got friction pulling him back, we've got T1 pulling him back. T2 is not pulling him back directly, so we don't account for that directly in here. It'll get accounted for when we calculate T1 though. Plus any acceleration that we actually want this thing to achieve. Great. Since T1 was back here, we had, which included, T1 included T2 in its calculation already, hence why it's already included in there. So great, we've got this plus the extra 1,000 A and the extra 1,000 from the friction. So we end up with 6,000 plus 6,000 times whatever acceleration you want. So basic idea with these is draw a picture, break it down into all the component parts. Hopefully it'll be nice and flat because that definitely allows you to cancel out a lot of it. Sometimes it'll be on an incline though, so bad luck, you're going to have to do a bit more work. But the same process holds. You just draw, figure out all your forces, start on the easiest case, which is usually the last carriage. Sometimes it's not, depending on what information you've got, but most of the time that's the easiest. Cool, so that's the force that this thing would have to deliver. If it's going to accelerate at all, then that's going to have to be. Beautiful. All right, over to this guy. So pulleys, slightly more fiddly a lot of the time. So I've given my masses A, B and C as 2 kilos, 3 kilos, 6 kilos, and again I'm making G10 just for nicer numbers because it's bad enough with the 10, much less with the 9.8. Cool, so we draw a picture, put in all our forces. Now, since we know that this is 6 and these two add to 5, we already know that it'll go that way, so I've got my acceleration going around that way. In certain problems you won't know which way it necessarily goes. You can usually have a fair guess, but sometimes you won't know. It doesn't matter which way you actually pick, just pick one to start because it makes your setup of equations easier. And then at the end, acceleration might turn out to be negative, in which case obviously it's going the other way. But you still just pick a direction and then go, cool, A goes in this direction, so if you get a negative A, it just means it's actually going in the other direction. Beautiful. So, as we did back here, try to focus on the simplest case first. In this case, I'm going to focus on A. You could have focused on C, but B would be the most annoying one, so definitely don't do that first. Cool. I'm going to pick A because first letter of alphabet. So I've got down and up. So we've got, since I've counted A as going this way, that's going to be the positive direction. So T1 going up minus G times M. So G times M. Great. Another equation for the force on B, similar story. I've got T2 going up, T2 coming down because they have to cancel down, and the mass of B, done. And similar story for C. Now, to make any progress here, we just have to realise that if this thing's going to move, all three things will accelerate at the same rate. Because if they didn't, then the string somewhere is going slack, and that doesn't make sense anymore, because then if the string goes slack, why is the piece accelerating at all? It doesn't make any sense. So all the accelerations should equal, so we've got these guys. We can set all of these equal, and now we've got this equation, which is essentially just simultaneous equations. The way I've done it, I've paired the first equation with the second equation, and then after that I've paired the first with the third. You can pair any set, it doesn't matter, but that's the way I've done it here. And this is just basic year 10 stuff. The numbers don't end up perfectly neat, but they're not terrible. Imagine if we hadn't have used that 10. At this stage, we've got all of our tensions, which is happy. We might want to know what the acceleration is, if that's what the question was asking. And so you can sub that into any of these. I would highly recommend sub it into all of them and make sure you get the same result for all three, or for as many bodies as you have, simply because it's very easy to do a dum-dum anywhere in this process, particularly flipping negatives, just because you're thinking, oh, this is going up, this is going down, but you want all of that to count as going up. So always check all three, just as a safety net. But But that's that. The hardest part about these isn't so much the math per se, it's about the setup. So draw a nice force diagram, be careful, set whichever direction is the positive acceleration, and then very carefully just make sure you write a statement, double check that it's perfect before you write another statement, and then eventually it just becomes blind math after a while. And then always, when you get your result for acceleration, just check that it makes sense for all objects. Cool, that's 13D. Send me an email if you get stuck. Bye.